Welcome back. The issue of making a system reliable when the components of the system themselves are unreliable appears very often in computer science. In this video, we will see examples of protocols that send messages reliably, even though the links that carry those messages suffer from transmission faults. The contents of this video are automatic repeat request or ARC and two ARC based protocols, stop and wait protocol and sliding window protocol. This issue of reliability is addressed at other layers in addition to data link layer. It's also addressed at transport layer and application layer. The principles of reliable delivery that we'll learn now is applicable at these other layers as well. By the end of this video, you would know how to provide reliable delivery in spite of transmission problems. We know from previous videos that transmissions are not always perfect. The received frames can have errors, and the errors cannot always be corrected either. If error correction is not possible, corrupted frames have to be discarded, and therefore it is the responsibility of a reliable link level protocol to recover from these discarded frames. Reliability is accomplished using a combination of two fundamental mechanisms, namely acknowledgements and timeouts. We are going to discuss these mechanisms in the next slides. An acknowledgement is a control frame that a protocol sends back to its peer to mean that it has received the sent frame. And we use ACK as a short for acknowledgement. When A sends data to B, if B receives the data correctly, it will send this ACK to A. And the receipt of ACK by the sender indicates successful delivery of the message that it sent. A control frame has only header and no data, and the receiver would sometimes send this ACK not separately but in addition to some data that it might be sending back to A, and that is called piggybacking. By doing piggybacking, it saves the overhead of sending an ACK frame altogether. The question that we ask is, what if A does not receive this ACK that B sent? And this takes us to this second method of timeout. If the receiver does not receive an ACK after a reasonable amount of time, then it retransmits the original frame. And this action of waiting a reasonable amount of time is called timeout. Now we will have discussion of what is a reasonable amount of time later, but for now, at least realize that it has to be at least as big as one round trip time. So this general strategy of using ACKs and timeouts together to implement reliable delivery is called automatic repeat request or ARC. Stop and wait is a very simple ARC protocol. In stop and wait, after transmitting one frame, the sender waits for an acknowledgement before transmitting the next frame. And if the acknowledgement does not arrive after a certain period of time, that is the timeout period, then the sender times out and retransmits the original frame. And it keeps doing that until it receives an acknowledgement, or the number of retransmissions exceed some maximum number. Before discussing stop and wait protocol further, we need to get familiar with packet exchange diagrams. These diagrams are a tool to visualize the interactions in distributed systems. This is a packet exchange diagram. In these diagrams, the time increases downwards. And for each entity that we are interested in, we draw a line, right? So suppose we have a sender and some receiver, and suppose it sends a frame and receiver sends ACK back to the sender. And so we have these two entities, sender and receiver, right? And for each entity, right, we draw an arrow showing any packet exchange, right? So for example, if here sender is sending a frame to receiver, so we draw an arrow starting on sender line to the receiver line, and these arrows are slanted to indicate that it takes non-zero amount of time to transmit a packet, right? So this is the time at which the sender sends, right? And in synchronized clock, this would be also the time at with respect to receiver's clock at which the sender sent this packet. And so this distance is to show that it takes non-zero time for a packet to travel from sender to receiver. And the second thing to note is that people don't usually draw these diagrams as calibrated diagrams with respect to time, but this is to show happened before or happened after type of relationship. And so what this diagram means is that the sender sent this frame to the receiver, and after the receiver received this frame, it sent an ACK back to the sender, right? And so a diagram like that showing this ACK would be wrong, because you can't send an ACK before you receive the frame. Suppose there was a third node, let's call it U, that R would forward this frame that it received from S, and then U in turn also sends, let's say, an ACK back to R. Then we would simply draw another line for U. And now note that the receiver cannot forward this packet to U before it has received. And let's suppose after receiving this packet, it first sends an ACK. And so what we're going to do is we will simply show this arrow from receiver to U, and we simply put this label to indicate that it's a data frame. And then this is an ACK that U sends to the receiver. And so we put these labels to indicate some properties of the packet that are exchanged and that's of interest to us. And we indicate events by marking things on this line. So for example, we show the timeout for the sender by drawing a line that indicates that this packet that was sent at this time would have a timeout here. So if the acknowledgement is received after this timeout, right, then before the acknowledgement was received, the sender would have sent the original frame as retransmission. And now we are going to understand the issues that arise in a stop and wait protocol using these packet exchange diagrams. So this first diagram we saw in the previous slide. Here the sender sends the frame and the receiver sends the ACK. Both the frame and ACK are received correctly and before timeout, and that's a happy situation. The second diagram shows the original frame to be lost. By lost, we mean that this frame either resulted in collision or the receiver received it and detected error on this frame, but it couldn't correct it. And so the sender is going to time out, and since it didn't receive an ACK from the receiver before timeout, it's going to send this frame again. And in this second time, the frame was received correctly and the receiver sends the ACK, and again that ACK is received before timeout. Now, not only the frames but ACKs can also get corrupted, right? So that's shown in this third diagram. So again, sender sends the frame received correctly by the receiver. It sends an ACK, but now the ACK is lost. And therefore the sender after timeout is going to send the frame again. And then the receiver sends the ACK back. Note that even though the receiver had ACKed this frame, it ACKs again. In the fourth diagram, showing the result of setting this timeout too early. And so sender sends this frame, receiver sends the ACK, but the ACK arrives after timeout, right? Remember this before and after relationship that these packet exchange diagrams show. And so because the ACK comes after the timeout, as soon as the timeout occurs, the sender sends this frame. And so this was unnecessary transmission just because the timeout was sent to be too small. Lost acknowledgements need to be handled carefully. As we saw, if the acknowledgement is lost or delayed in arriving, the sender will time out and it will retransmit the original frame. And the receiver will think that it is the next frame since it has already correctly received and acknowledged the previous frame. And the result of that would be that duplicate copies of this frame is going to be delivered to the network layer. This duplicate frames problem is solved using sequence number. So what happens is that the sender uses a 1-bit sequence number, right? So it's 0 and 1. So sender would send first frame, let's say frame number 0, then the receiver would acknowledge that frame saying I received frame 0. And then next time the sender sends frame 1, the receiver acknowledges that as acknowledge 1 and frame 0 and so on. And so now when the sender retransmits frame 0, right? So suppose that, let's just redraw on this one. So let's suppose that this ACK was lost, right? And so now when the sender is going to send the next frame, right, it's going to say frame 0 because it's retransmitting that frame, right? Now receiver already had received frame 0. It was expecting frame 1, right? But it didn't. Instead it received frame 0, so it will simply discard that. But then nevertheless it would send an ACK, so ACK 0. And so basically by doing this, there is no ambiguity at the receiver side whether the frame is the original frame or whether the frame is retransmitted frame, right? And as you can imagine, if this is the sequence, then next time the sender is going to send frame number 1 and it's going to acknowledge that frame as ACK 1. The main disadvantage of stop and wait is that the sender has only one outstanding frame on the link at any given time. And by outstanding, we mean frames that have not been acknowledged yet. And this may be far below the link's capacity. So a stop and wait is suitable for only low data rate networks. Consider this example of a 1.5 Mbps link with a 45 millisecond round trip time and 1 kilobyte frame size. The delay bandwidth product on this link is 1.5 times 10 to the power 6 bits per second times 45 milliseconds, and that gives you 67.5 kilobits or 8 kilobytes. But we are sending a 1 kilobyte frame, and therefore we are utilizing the link only 1/8 of its full capacity. Right? To fully utilize, we could have 8 frames outstanding. There's another way to come to the same conclusion by comparing the sending rate with the data rate. So the sending rate is the bits per frame divided by the time at which we are sending one frame. So we are sending a frame of size 1 kilobyte. So that is 1024 times 8 bits. And we are doing this every 45 milliseconds. And so we divide by 0.045. That gives us 182 kilobits per second, which is less than 1/8 of 1.5 Mbps. This analysis suggests us that we should have 8 outstanding frames on this link to fully utilize its capacity. And so our next protocol is sliding window protocol that allows multiple outstanding frames. The sender assigns a sequence number to each frame. So let us say the sender keeps 5 outstanding frames. So this would be frame 0, frame 1, 2, and this is frame 4. And so it can't send any frames without receiving an acknowledgement, because it has already sent 5 frames and hasn't received acknowledgement for those frames. And so as soon as the acknowledgement for this frame 0 arrives, the sender can send another frame. So this would be, frame 6, and then the acknowledgement for frame 1 arrives, and it can send frame 7 and so on. Think of the transmissions of sender as an array of frames. And so at any given time, let's suppose, as we said, the sender can have 5 outstanding frames. So basically it sends these frames 0 through 4. And after that, it has to wait for an acknowledgement. And now once the acknowledgement for 0 comes, then it has now 4 outstanding frames, but it is allowed to have 5 outstanding frames. And therefore it shifts its transmission window to the right? And that means now it's eligible to transmit frame number 5. Now once again the acknowledgement for frame number 1 comes, it can do the same thing again, and now it's eligible to send frame number 6, and so on. And so basically we are sliding this transmission window, and that's where this name comes from, sliding window protocol. And so the sender needs to maintain these three variables. One is the size of this window, that's called sending window size. Then it has to maintain this pointer that says the last frame that was acknowledged, right? Last acknowledgement received, and also the last frame sent. And so that's basically what is listed here. So sender maintains these three variables: sending window size, or SWS for short, and this is the maximum number of unacknowledged frames that the sender can transmit. The second is the last acknowledgement received, or LAR, and it's the sequence number of the last ACK received. And the third one is last frame sent, and that's the sequence number of the last frame that was sent. So in this illustration, the sending window size is 7. The last acknowledgement received is frame number 4, and the last frame sent is 11. So when an acknowledgement arrives, sender moves the last acknowledgement received to the right, and it can now transmit another frame. So let's suppose that the acknowledgement for 5 comes, so LAR is going to point to 5. Now the sending window is going to shift again to the right, so from 6 to 12, and now the sender can send frame number 12. Right, so if it sends frame number 12, LFS is going to be equal to 12. And so sender maintains this relation of LFS minus LAR is less than or equal to sending window size. Equal to should be clear from this example, less than because it may be the case that, for example, sender didn't have any more data to send, and therefore now LFS still remains at 11, right? So it doesn't have anything to send, but LAR now shifted 1 to the right. And then the next acknowledgement comes, then it would move to 6. And if there is no further data, then it will keep shrinking, right? So although LAR keeps increasing, LFS remains the same, and therefore it can become actually 0, because all the frames sent are also all the frames acknowledged. The sender associates a timer with each frame it transmits, so that if it does not receive the acknowledgement for that frame, then it will eventually time out and retransmit that frame. The second thing to note is that the sender has to buffer SWS worth of frames, or should rather say the sender has to buffer up to SWS worth of frames. So all the frames that are outstanding, right, has to be buffered at the sender, because any one of these outstanding frames, right, may result in corrupted frames, or maybe the ACKs for them would get lost. And so the sender has to be it has to be possible for the sender to retransmit when that happens. As the receiver gets frame, it sends these frames to upper layer. So suppose in this case it received frame 3 correctly, and so it basically sends to upper layer, and similarly for frame number 4. But suppose frame number 5 was corrupted, right, and then after that it received frame numbers 6 through 9, and so the receiver cannot really forward these frames to network layer, so it needs to buffer these until it gets frame number 5. And so that is captured in this receiving window size, or RWS. And so this refers to maximum number of out of order frames that the receiver can accept. And in this example, this is same as what we saw before, but it does not have to be. Receiving window size could be just 1, which means that receiver does not buffer. And then it maintains these two bookkeeping variables: last frame received, which is in this case frame number 4, and it also maintains this largest acceptable frame, and in this case that would be 11. Right. And what it also means is that this receiver is not going to accept anything beyond that. And so receiver maintains this relationship of the largest acceptable frame minus the last frame received is less than or equal to the receiving window size. Now, if a frame with sequence number n arrives at the receiver, then these are the rules that determine what the receiver is going to do. If n is less than or equal to LFR, means it has already passed these to upper layer and it has acknowledged, then it simply discards these. Or if the sequence number is bigger than the largest acceptable frame, then it also discards this. So suppose sender sends 12 and 13, so it simply is going to discard that. So if it is greater than last frame received but less than or equal to largest acceptable frame, then it would accept that frame and it would buffer it. And it may or may not send an ACK depending on several ACKing schemes that we will discuss. But if the frames are received in order, it will send an ACK. In our discussion so far, the receiver was acknowledging frames individually. In cumulative ACK, when the receiver ACKs, let us say some frame n, what it means is that it's also acknowledging that it has received all frames with sequence numbers up to n. Consider this example where last frame received is 5. So this is LFR. Receive window size is 4. And therefore the largest acceptable frame is 9. And suppose 6 and 9 both are missing. So the receiver basically has to buffer 7 and 8. 7 and 8 has they have arrived, but 6 is missing. And so the receiver is not going to send any ACK until it receives frame 6. So sometime or later the sender is going to time out, and the frame number 6 is going to arrive. And in cumulative ACK, the receiver is going to simply ACK frame number 8 right away. So rather than sending 3 ACKs for 6, 7 and 8, it will send an ACK for frame number 8. So this is our new last frame received, and since our receive window size is 4, so this window size will shift 4 to the right, and our largest acceptable frame is also going to shift, and is going to shift by receive window size. Yeah. And so that's what this is explaining. So when receiver acks frame number n, it implies that the last frame received is n, and the largest acceptable frame is this last frame received plus the receiving window size. And because of that, throughput suffers. And the longer the timeout, the more severe this problem becomes. So how to improve this? We can improve this by providing early frame loss feedback. And there are two ways that we are going to discuss. The first is called negative acknowledgement, or NAC. And the second is selective acknowledgement, or SAC. Just note that both of these add extra complexity to the protocol, and the inequality that we saw, last frame sent minus last acknowledgement received is less than sending window size, need not hold. In negative acknowledgement scheme, the receiver informs about missing frames by sending NACs. So in the example that we discussed, we had frames 7 and 8, but frame 6 was missing. And so in this case, the receiver will send a NAC for frame 6 when frame 7 arrived and when frame 8 arrived. NAC requires us to invent a new frame, and it's extra complexity. A better approach is to send duplicate ACKs, and in any case our goal is to simply send a feedback to the sender that we didn't receive a particular frame, and this approach works just fine. And so with these duplicate ACKs, what we would have done is when frame 7 arrived, we would have ACKed frame 5. And then when frame 8 arrived, we again ACK frame 5. And therefore, the sender knows that frame 6 is missing. In selective acknowledgement, the receiver ACKs exactly those frames that it has received. So in the example that we just saw, we saw that frame 6 was missing, but frames 7 and 8 were received correctly. So the receiver is going to acknowledge these frames 7 and 8, and sender would know that frame 6 is lost. And therefore, at the cost of additional complexity of maintaining the list of frames that are yet to be acknowledged, sender can keep the pipe full. Selective acknowledgement is used in TCP. The next, we discuss selecting the window size at the sender and receiver. On the sender side, the sending window size could be at most the delay bandwidth product, round trip time times bandwidth, divided by the maximum frame size. And note that in different networks, these two parameters, round trip time and bandwidth, can vary with time. On the receiver side, the receiving window size can be anything from 1 to sending window size, or even more. When receiving window size is equal to 1, that means the receiver will not buffer the frames that arrive out of order. And when receiving window size is equal to sending window size, that means that receiver can buffer any of the sent frames. However, although receiving window size could be larger than sending window size, but it is really not useful, because then the extra buffer that the receiver allocates will not be used. Thus far, we had been assuming that sequence numbers go to infinity, but actually we send sequence numbers in header, and as we know, headers have these fields, so size is fixed. So if we have an n-bit sequence number field, then our sequence numbers could go from 0 to n max minus 1, where n max is 2 to the power n. Now suppose n is equal to 2, then the sequence numbers would go like 0, 1, 2, 3, and then another incarnation of this 0, 1, 2, 3, again 0, 1, 2, 3, and it continues like that. The size of the sequence number field is determined by both sending window size and receiving window size. To see that, let's just consider one example of setting nmax equal to sending window size, and suppose sending window size is 3. And suppose sender sends these frames 0, 1, and 2. Receivers receives all of them correctly. It sends these ACKs, but the ACK for frame 0 is lost. Now after some time, sender is going to send this frame 0 again. So let's just say it sends here. And then after that, it might send the second incarnation of other frames. And on the receiver side, the first frame is 0, 1, and 2. Since it acknowledged them, so the second transmission of the original frame 0, so this is a retransmitted frame, is going to mistake that one as the second incarnation of 0. And so clearly setting nmax equal to sending window size is not sufficient. And so what we need to do is we have to set nmax at least as big as sending window size plus 1. Now suppose sending window size is 3, but we increase nmax by 1. So nmax is 4. Our sequence numbers are 0 through 3, and then 0 through 3, and so on. And suppose a similar situation as before, the ACK for frame 0 is lost, ACKs for 1 and 2 are received fine. Now the sender is not going to be able to increase its transmission window, so after some timeout it will send this frame 0 again. Now on the receiver side, it received frames 0, 1, and 2. Now it is expecting frame 3, but instead it receives 0, and therefore it discards this frame. Next, we are going to see that this nmax being greater than equal to sending window size plus 1 is insufficient if we increase the receiving window size. So now suppose we increase the receiving window size to 3 and we keep nmax equal to 4. Now suppose sender sends 3 frames 0, 1, and 2, but both of all 3 ACKs are lost. And so all of these ACKs are lost. And so it's going to retransmit these 3 frames again. So it's actually retransmission of the same frames. However, on the receiver side, it's going to it's going to be frame 0, 1 and 2 from the first incarnation. Now receiver is expecting frame 3, but it can buffer up to 3 frames. So when it receives this 0, it's going to treat this as the second incarnation of the frames, and it's going to actually accept, although it is expecting 3, so it's going to reject this one. So Nmax must be at least as big as the sum of sending window size and receiving window size. So from our discussion of sliding window protocol, it should emerge that this protocol plays 3 different roles. Number 1, it provides reliability. Number 2, it preserves order. It only passes frames in the increasing sequence number order, and it buffers out of order frames until the missing frames are received. And thirdly, it provides flow control. Flow control is a mechanism by which receiver can control the rate at which the sender sends data. And by setting the receive window size to a small number, it was what the receiver was doing is that it was sort of doing this flow control. It is also possible that the receiver can inform the sender about how much buffer it has available, and that we will see later on when we discuss TCP. To summarize, we discussed stop and wait and sliding window protocols that implement ARQ, automatic repeat request, and automatic repeat request uses these 2 fundamental methods to provide reliable delivery, and those are number 1, acknowledgement, and number 2, timeout. Too small a timeout causes repeated transmissions, and on the other hand, too large a timeout can cause the throughput to suffer because the sender will remain idle. Thirdly, stop and wait allows only one outstanding frame, which may not be suitable for applications that send large amount of data. And lastly, sliding window is a general reliable delivery method that provides in-order frame delivery and also flow control. For further reading, the material that we covered is discussed in Chapter 2, Section 5 of Peterson and Devi, and Chapter 3, Sections 3 and 4 of Tenenbaum and Witherall. Here is a quiz for you. Find out which of the following options are correct. You might want to pause this video before seeing the answer in the next slide. The correct options are A, C, and D. In stop and wait, if a corrupted frame cannot be recovered, the receiver does not send an ACK, and that is correct, because when the receiver sends an ACK, it means that it has received the frame correctly. If a receiver receives duplicate frame, it must be that ACK was lost, and that is not correct, because there is another option when that can happen, and that is when timeout occurs. So this is not correct. C says the receiver maintains largest acceptable frame minus last frame received less than equal to receiving window size. That's correct. And D says the condition receiving window size equal to 1 implies that the receiver does not buffer any frame, and that's correct. That's all in this video. See you next time.